Okay, so now we're moving to a general discussion, and I want to kick it off with one question that I have for all of the presenters. And if you follow my writing, you might be able to predict this question. So you all talked about stuff that I believe was tested against English data. I think Sam was the only person to utter the word English. So tisk the other two of you. Correct me if I'm wrong, the recordings will correct me. And my question is, what would change if you tried these ideas with a very different language? And by very different language, I mean, what about ASL? What about Inuktitut? What about, let's say, extremely isolating Vietnamese and highly inflecting Turkish? So maybe Sam first?
Sure. So as I was talking mostly about data, I think that you could make very similar data for any arbitrary language. I didn't talk as much about methods. The methods that I did present, some of them use trees, some of them use RNNs. Empirically, what we found for English is that difference doesn't turn out to be that important. Switching into total speculation, I think my hunch from what I've observed is that RNNs are sort of on the better side of mediocre for a pretty wide variety of tasks in NLP. Admittedly, most of this evidence is in English, but my suspicion would be that if you can get the input encoding right, that RNNs would continue to be on the good side of mediocre and sort of serviceable, and you get roughly the same pattern of result for pretty much any language. The input handling issue could be huge, though, because dealing with things like sort of simultaneous channels of information in ASL or languages with really rich morphology, just turning things into a sequence of words is going to be a big project.
So yeah, I guess the answer, at least for the module net stuff, is that we kind of defer to the semanticists in that respect, and to the extent that the field already thinks there are kind of like primitives and has ways of producing analyses for those things.
I'm going to ask that.
Exactly, right. No, that we can kind of respect those. At the same time, like, again, ASL, especially where there's like explicit variable binding and kind of scalar things that don't show up, you might need additional tools from what we have right now, but I think what those tools are is spelled out by the theories that are there already.
Yeah, I'll say I followed Chomsky 1957 and said, well, English generalizes to everything. But just kidding. So first, we have done this on lots of other languages. We are somewhat, with RNNGs in particular, we're of course limited to the fact that there aren't a great number of phrase structured tree banks out there in other languages. The situation with dependencies is, of course, much better these days. Watch this space for some interesting stuff there. Yeah, no, I think this, so we are thinking quite a lot about what these typological differences mean, and in particular, sort of the order that we use to build trees, the predictions that are made for what's going to be difficult if you're building a tree top-down versus bottom-up. I mean, this basically transfers what we know from parsing, transfers very nicely to this kind of generative view of the world that we've got. So we would make some predictions that say this top-down build order is going to be quite hard for Japanese, right? This all planned work, but yeah, you're absolutely right. And this is, of course, I mean, I probably more than these other two are really making a claim about sort of general inductive biases for language. So I absolutely do need to and should run these experiments on other languages.
Thanks. So other questions for our panel?
Good skill dashboard for something.
Yes.
I'm just wondering if you have some sort of a common sense for when trees help, because the evidence seems to be mixed. We've heard both just in this one session that they make a small difference, and they should make a big difference for agreement. I mean, you do not get fantastic results for long dependencies, but so what is the bottom line of the value of having trees as opposed to strings?
Well, we got about human level performance, I would say, on long distance. We got superhuman performance for the short range dependencies. I don't, really know what to make of that. But it's edited text. But I think we are at ceiling really, so it's one thing. I think again trees are going to, they come up in two cases. One is in small data scenarios. We have universal function approximaters. We have Turing complete computational power. We have fairly good learning algorithms. If you have enough data, it is completely uninteresting to me that you can learn to translate with these models with a million words of parallel text. What's interesting to me is, can you learn to translate with a reasonable amount of data, or can you learn to, say, ground natural language or reason about entailment with quantities of data that would be somewhat commensurate with what a child were exposed to, rather than, lifetimes too much data.
Yeah, I mean, I guess I'd just say to that also, there's not just one way to use trees, right? That there's the setting where your model has some sort of explicit latent tree structure, but it's never spelled out what to do with it. There's the model has an explicit tree structure that's sort of supervised in the training data, and you force it to respect that. And then there's sort of the paradigm where you write down a tree somewhere and you don't care whether the model actually uses it or not. And I think we have examples of all of these things. I guess I'm actually fairly pessimistic in the long term about models that are forced to march in lockstep with a tree according to a representation that someone has written down. But certainly in the small data settings, we know with our engineering hats on that they're useful right now. And I think in the long term, as a kind of scientific tool for figuring out how can we get these kinds of biases in other ways into the model without locking things down too much. They're a powerful tool.
I don't disagree with any of that. I just have my little heap of evidence from NLI land. What we've seen there is looking at sort of relatively simple models where you can isolate what's going on. Models that use tree LSTMs and use sort of externally supplied Pendry Bank style trees and plain RNNs are about equivalent. That at this scale of maybe hundreds of thousands of training sentences, the sort of inductive bias given by trees seems to be roughly canceled out by, I'm not sure exactly what makes them do worse in some examples. Maybe it's that inductive bias is wrong in some cases because we're using Pendry Bank style trees, but they're roughly equivalent. If you build some sort of hybrid model, it's often possible to get trees to do a little bit incrementally better. But that's sort of a fleeting phenomenon. We'll sort of see if you take a simple model and bolt trees on in some way, that almost always helps. If you take a very complex, very powerful model that can learn to do anything and bolt trees onto it, it usually doesn't make much of an empirical difference.
It's more of a comment, but I think that the example that Chris was showing, that the empirical difference is going to come out only in the long tail. So if you just average across a randomly sampled set of examples, you're not going to see it. And the other comment that I was going to make is that even the examples that Chris took from our paper, I think, are not necessarily the most difficult examples for models. And for agreement specifically, we found that whenever there's a relative clause, for example, the models do much more poorly than if the attractor is in a prepositional phrase. And I can explain why that is. I don't want to get into too much detail, but I think that you really need to make sure that you're looking at the most challenging cases to know whether this additional layer of adding trees to the model helps or not.
So I want to turn that around to a question. Given the kinds of data that you each were looking at, where are those most challenging cases? So in the agreement thing, maybe Tal's answer covers it, but in the, I don't have a 3-word summary of her work, but in SLI, what is the most difficult sort of long tail stuff that maybe linguists would be most interested in?
So I think I attempted to answer this a little bit in the questions this morning, but I think for textual entailment, we're kind of stuck in this position of not having a sharp boundary between the semantic work and the sort of reasoning work, which gets into common sense knowledge. And so I think this is this is maybe not that linguistically interesting, but as a matter of kind of getting NLP tasks done, I think this is actually a pretty big open issue in NLP, is how do we bring in world knowledge? How do we get the kind of world knowledge that a typical speaker needs in order to understand language? Zooming in to the level of individual phenomena, I think all the things we think are hard, but I don't have too much interesting to say there.
And Jacob, what do you see as the hard cases?
Yes, I mean, I guess maybe in the same way, it's not even clear that it's the hard things are like linguistic as such, so much as things that language is telling you to do. And this gets a little bit into the point that Paul was making, that sort of really complicated quantification phenomena and hypotheticals and counterfactuals and all these sorts of things seem to be kinds of reasoning problems that just like generically this sort of neural machinery is not great at right now, but that's possibly not an axis that's necessarily linguistically interesting.
Yeah, I guess my general feeling is that we have to be careful about concluding too much about sort of the power of these models from the tasks that we read about on arXiv, which have been carefully selected because they've done well. And tasks are routine. I just published a paper on a very difficult reading comprehension task, and one of the reviewers was like, well, this is too hard, so therefore, no neural net would, it would be bad to have this as a task. It might basically embarrass us. This did come up in a review from a prestigious journal. There are maybe some methodological or sociological effects that are making these models look better than they actually are.
Matt Goldrick from Northwestern. I wanted to maybe try to invert the question a little bit. So as linguists, we, myself included, have been very interested in the long tail. What are the lessons from researchers who are not focusing on the long tail for linguistics that you think? So when you're focusing on the most commonly observed cases, are there insights that you're getting not from focusing on the edges, or simply none?
I mean, pattern matching with no theory behind it gets you a really long way. And I think, as has been said again by Sharon before here, like a lot of what these neural methods are doing especially is just learning sort of good similarity functions and doing well with respect to them. And this is, you see this even, like everyone got very excited about all these image captioning tasks a little while back, and look at these sort of deep compositional representations of images that they're building up to be able to generate, captions that are like the pizzas on the pan on top of the pizza oven or whatever. And then you go look in the data, and there are 3 captions that say the pizza's on top of the pan on top of the oven, and you can do really well with the nearest neighbor baseline in the appropriate feature space once you have, 100 million examples of whatever it is that you're trying to do.
What Jacob said.
So, when a class of model is supposed to be really good at machine translation, the sequence-to-sequence models, and they are indeed much better at machine translation at the maybe scale of data that English to Spanish or Chinese machine translation systems have to train on. But in the smaller scale, for example, in our study on question formation, it was actually extremely difficult to get them to do something reasonable. So I think that it's not so clear what we can conclude from. I'm just echoing what people have been saying. That it's not so clear what we can conclude from the training regimes that people have in NLP to more cognitively realistic training regimes and training set sizes.
I want to make one other point that I think we've seen as we've gone from what we've seen in neural nets is basically a world where we've gone from models where we made our own independence assumptions based on data analysis, linguistic theory, introspection, all of this stuff. So case in point would be context freeness. It's an independence assumption. And for example, what this model did is it said, well, I'm going to completely dispense with that, and the RNN that's controlling this generation process, it's up to that to figure out what the independence assumptions are. Now, there are certain biases there, but the very top of the distribution of very frequent stuff, there's enough sort of noise around the edges that violate these independence assumptions that we've started with. And all of the models we used to work with, I think, were actually quite good at long tail stuff. And we still see that. If you look at sort of the performance of a phrase-based machine translation system compared to a neural net one, very long sentences continue to do better. Like extremely long sentences still on phrase-based systems, or at least they're indistinguishable. And so it's really that we were thinking about kind of the regular case, and what I'm trying to do is say we want that to be sort of a good basis. We want that to be the bias, but we want the model to be able to violate this as much as it wants. And the old models we had, you had no choice but to adhere to them. And that's the big lesson that I've had. I don't know if it's from working on the sort of top of the distribution, but in the switch from sort of highly biased models to models that learn their own biases, or some kinds of their own independence assumptions, I should say.
I totally agree, but I might want to frame this slightly differently in a way that might make things sound a little bit worse, which is I've worked on a bunch of problems that involve, in various ways, trying to inject kind of linguistically principled bias into machine learning systems for NLP tasks. And very often you have a subset of the data, you have a long tail phenomenon that you're interested in and you're targeting, and it's very easy to show that the thing you're doing will help performance there. And what almost always happens, this is a graveyard of unpublished papers, is you find a way to do quite measurably better on the phenomenon you're targeting, and you do half a percentage point worse on everything else because you've slightly hurt the learning process in general, and you wind up with a negative result.
All right, I've got one more in my pocket. I want to prompt you guys to do some speculation about what's a task that would show general purpose NLU, and even if you can't answer that question, what do you think the role of semantic compositionality is in general purpose NLU? And I know, Sam, maybe you might start because your task is sort of close to that, but I think maybe not quite general purpose.
Just a quick translation for natural language understanding,
yes.
right? Okay.
Yeah. So I'll keep sort of waving my banner and arguing that textual entailment requires pretty comprehensive language understanding, and I think we will need to. We will need, if our models are to do well on the long tail of textual entailment, you will need to get compositional semantics right. Whether that means the model will be very visibly, overtly doing compositional semantics, I don't know, but they will need to, if they're going to generalize, either explicitly or under the hood, be working out reasonable internal representations for parts of sentences.
I'll say explanation. I need models to be able to explain what they're doing and also understand an explanation in order to sort of replicate something. I had a fortune to work with a wonderful PhD student, Wang Ling, who had a paper on solving algebraic word problems last year, and he created this interesting data set where he crawled a bunch of forums on the web and had where people would like pose questions and say, how do you solve these, and then crawl the rationales. And he learned to answer these questions by reading the rationales, and he actually built a generative model of the rationales. So this model would not only then, you'd say, the two trains are traveling in opposite directions or whatever, but then it would spit out actually a text description and a latent program that was doing this. And going through this exercise, I mean, it was great. This is a model where sort of sequence to sequence kind of models, I mean, they just fall on their flex. I mean, it's exactly 20%. It's a multiple choice thing. They get exactly a chance when you do sequence to sequence. But when you start generating explanation and you have the model can actually do arithmetic operations internally, suddenly you start doing really well. But you need that explanation to drive things. And I really think explanation is sort of the fundamental aspect of understanding. It's the only thing that shows understanding. Everything else I mean, I don't know what it means to understand something unless you can explain it.
And so how does compositionality fit into solutions?
Oh. It's important to.
Yeah. I mean, truly, I have no idea what task would actually capture the general problem, and I think if anyone knew it, they would be working on it, and maybe they already are. As far as compositionality goes, again, I guess clearly there is something about the structure of the world that makes compositionality a useful bias for these kinds of models to have. What it is about the structure of the world that makes that true, I don't know, and whether it's something that we can sort of explicitly write down by hand, or whether it's just something that we have to learn from a bunch of other related problems to sort of get access to that right structure, I don't know. But yeah, I guess I would be surprised if 20 years from now the kinds of models that we're building for natural language understanding, whatever that means, have like an explicit discrete compositional mechanism in the inside.
Sorry, you would be surprised if they do or don't?
I would be surprised if they do.
So we have a pretty serious difference of opinion there, it sounds like.
Yeah, I'll say I think I think they'll be implemented on something sub-symbolic, Paul style. But I mean compositionality is, I think there are good reasons. Nature has invented compositionality, or at least combinatoric optimization a number of times, not just in human language. Adaptive immune system, DNA, things like that. I mean, there's clearly, this is not like an artificial thing that doesn't exist in nature and we've just imagined it because we're weird linguists or something like that. This is a solution with principled reasons for solving real problems. It has to do with statistical efficiency and it has to do with flexibility. So, discrete infinity and all of that. I think, yes, it may look squishy on the edges, but it will be functionally combinatorial.
So yeah, I absolutely agree with everything you just said, but do you think that there's going to be anything that we, either anything that we will be doing as model designers to encourage that behavior outside of our choice of data sets, or do you think there's going to be anything inside the models that we can actually point to and say, like, there's merge?
Well, I mean, I don't know behaviorally, yes. Whether we'll be able to understand the substrate on which that's implemented, understanding, maybe beyond our ken to sort of grasp that, but it'll be there. My guess is actually, and we will be able to see something, we'll be able to introspect better with these models.
We'll build it before we can explain it.
Yeah, but I think we will build it before we can explain it.
Yeah. Yes.
Christine, UMass, coming back to the question right before Emily's, so you're getting into talking about when are, for instance, trees useful, and what came up was, oh, you have small data sets. And then someone's talking about pizzas on tops of microwaves and refrigerators or something. So I guess what I was wondering, I think there might be, when you have a small data set, you won't sample the long tails or something like that. Or if you have a big enough data set, you can just kind of memorize things. So where I'm going is for Matt's question, for what the lesson is from, I don't know, people like you or something, for a linguist, I'm wondering if one answer might be, you could use your methods, but then if you're interested in these long tail phenomena, really hand tailor what input you use, not necessarily like say the size of the data, but also the quality of the data and the constructions and so forth. And then using the tools that you're developing, like these RN grammars and so forth, hopefully find insight for what having that in the input might change about your generalizations. Do you think that's something that linguists can learn from, or is what you get interpretable enough for a linguist to scientifically learn from that?
So one thing I haven't shown here that you can do is you can ask for a given prediction, for example, what are the inputs that are most strongly determinative of that particular prediction. So you basically, normally we think of, we run back propagation to get the derivatives of the weights, and that's how we optimize the, whatever our loss is, minimize it. You can also differentiate with respect to the input representations, and you can say, well, what is it about the input that's making it want to predict this? And often you find very strange things that, it's not paying attention. So they do this especially in computer vision, where they say, what's sitting on the bed, and you visualize where, what parts of the image are being looked at to generate the answer, and it's looking at the curtains and it answers cat. Well, it's just figured out that cats sit on beds, so going to this sort of stuff. So, but you can use this. In positive cases to say, well, we don't always have a good sense of sort of what the covariates are that are sort of giving rise to a particular decision, and I think these tools can be useful for linguists. So, for example, if you're modeling, say some difficult to analyze phonological, grammar problem, you might be surprised. You might say, well, we analyze this traditionally as harmony, but actually say there's some other explanation for why a particular vowel form is appearing. Could be one example, because it looks like the gradient is, pointing somewhere else. It's not on the other vowels, say.
I'd say also maybe a sort of pessimistic rephrasing of the first part of your question is that we always memorize the data set with these kind of generic models. When the data set is small, we memorize it, and that's a bad thing. When the data set is sufficiently large, we memorize it, and that's a good thing. And the only sort of recourse that we have right now is building in these kind of explicit discrete structures, and that always hurts on the fringes in the way that these people have been describing.
So I'm going to quickly offer everyone who's not in the machine learning community a grain of salt to use when consuming machine learning community results. I think it is a like article of faith and deep importance, and like item 1 on the ethical code, maybe not ethical, but code of practice in machine learning, that train test split design is really, really important. But it's like an article of professional practice that we're actually not very good at following. So if you're doing image captioning and you have a massive set of images from a relatively constrained distribution where they're pretty repetitive, and you just randomly sort of cut that data in, and you take 10% of that data, and that 10% is your development set. You're choosing models based on how well they do on this held out 10%. If it's really a completely random sample of the data, and the data is pretty repetitive, these problems are really serious. If you can find some way to be a little bit more creative and find data that is representative of the problem of interest, but somehow a little bit different from your training data, maybe was produced at a later date in time or something like that, that will make the benefits of the kind of worst, most boring kinds of memorization go away, and will encourage you to build more interesting models and think more about your biases.
So with that savory, maybe salty remark, we should end this. Thank you very much.